Hello, and welcome to AP Daily for AP Physics C, Electricity and Magnetism. We are talking about topic 9.2, electric potential. This is daily video 5, and in this video, we will explore the relationship between equipotential lines and electric field vectors. I am Michelle Strand. I am coming to you as an Einstein Fellow on Capitol Hill in Washington, D.C. So let's quick review a little bit. Let's talk about equipotential lines. So equipotential lines are lines of equal potential. You've seen these on weather maps where they show you the weather and they show lines on the screen on the map. And those lines are called isobars. They're lines of equal pressure on a map. And when those equipotential lines are really close together, or the isobars are really close together, you're going to have a strong difference in pressure over a very short space, and wind moves from high to low pressure, and so you get high winds whenever you see those isobars really close. The same idea happens here with electric potential, that if those lines are really close together, that means the potential is changing really quickly in a small space. You can think of this also as like a steep hill. And then the change in potential over a distance is what we know as the electric field. So anytime you have a big change in potential over a small space, that's going to give you a big electric field. And the electric field lines are drawn perpendicular to the equipotential lines and always move in the direction of high potential to low potential. So think of downhill. So let's take a look at an example. So looking at equipotential lines, here I have a scenario. I have a bunch of equipotential lines. So this line here is all 4 volts. This one's here is all 3. And I want to rank the 4 points, A, B, C, and D, from largest to smallest electric field. So keep in mind that the closer those lines are together, the stronger the electric field is going to be, because you have a big change in potential over a small space. So I would say that A is probably going to be the biggest electric field because its lines are a little closer together. I would say that B and D are probably pretty close to the same if I look at their potential and the distance that those lines are. And then I would say that C would have the smallest electric field because those pieces are the farthest away. So sketching the direction of the electric field at points A, B, C, and D. So to justify, I have to draw the lines perpendicular to both of the equipotential lines that are near it. And I have to draw it from high to low potential. So if I look at A is going from 2 volts to 1 volt if I have the arrow down. B, because of the way the lines are, right, trying to keep perpendicular, again, going from high to low potential is going to point in that direction. C from high to low is going to get perpendicular here, got to go through point C and perpendicular here. Right, so I just have to be perpendicular when I go between those equipotential lines. And then D going from high to low is going to go here because the highest is the biggest positive, the lowest is the biggest negative. And so the electric field at D is going to point in that direction. So we can do some more practice. So here we've got a set of equipotential lines, and we want to know what are the signs of the point charges. So we assume there's a point charge at the center of these sketches of equipotential lines. Because this is positive voltage, the only way you get that is if you have a positive charge at the center. So the one near X is going to be positive. The one near Y, because I have this negative potential, is going to be negative. Why? Because the potentials are positive and negative. And now using electric field vectors to help you draw an electric field connecting points X and Y. So the assumption is if the point charge is here, right, that you get less and less potential the farther away you move. And so if I'm thinking about the electric field right here, and then the electric field has to be perpendicular, right, to both parts. And so it comes out perpendicular, but then it's going to be sort of drawn to this Y. And so you're going to get kind of this arc for that electric field line. So some additional practice here, we want to rank the electric fields at points A, B, C, D, and E again, from largest to smallest. So if I look clearly, B has the lines closest together. E's probably next. Again, looking at how close those lines are there, I would say probably A and D are about the same. And then C on the way outer edge here is going to have the smallest electric field. Again, because the equipotential lines are farther apart. Calculate the electric field midway between points D and E. So the electric field is just the change in the potential divided by the change in the distance. Right? So from D to E, the change in the potential is from 10 to 5, so 5 volts. And that distance is 1 centimeter, that's 0.01. And so this is going to be 500. And I can do volts per meter, or the other electric field unit is newtons per coulomb. And then the final piece, number 3, is what can you tell about the point charges based on this pattern? Well, it sure looks to me like these are both positive charges, because the potentials, right? If this is a line of +5, it goes all the way around here. So I've got positive potentials here and I've got positive potentials here. So it's fairly obvious, or should be fairly obvious, that the two charges have to be positive. So what should we take away? That equipotential lines are lines of equal potential. Very similar to isobars are lines of constant pressure on a weather map. The closer together the lines, the bigger the electric field in that region. Very similar, if you have isobars, those pressure lines close together, you have high winds. And electric fields run perpendicular to the equipotential lines. They will also always go from high potential to low potential. Hope that was helpful. Thank you and have a great rest of your day.